In a previous lecture, we talked about how we could use the sum of squares identity to separate variation in an experiment and prepare to construct a test that would compare means of different groups. In this lecture, we'll see exactly how to do this, how to construct the test statistic, and conduct the test. So the first thing is actually constructing the test statistic. Let's talk about the design that we used, because this will lead us to the test statistics. We're using the very simplest of design, what's called a completely randomized design, or one-way ANOVA. In this design, all experimental subjects are considered to be exchangeable. That is, there's no significant difference among them. And subjects are assigned to the treatments completely at random. So now let's look at the table, the way that we're going to find the test statistic. We're going to separate the variation into treatment and group components. So that was that sum of squares identity. And then we'll compare variances. We'll use those to construct measures that look like variances. And those will go into the computation of the test statistics. So here's our sum of squares identity right here. And then with each of those sums of squares, we have an associated degrees of freedom. There's k groups, there's k minus 1 degrees of freedom for groups. There's n minus k degrees of freedom within the groups, since we've eaten up k means. And then we'll just take the difference of this, or sorry, the sum of this. We'll have k minus 1 degrees of freedom overall. So the treatments row is also called between groups variation. The groups row is also called within groups variation. And then this s squared here, this is the overall variation for the experiment. So let's go ahead and apply this and see how this works. Here's our experiment. The pet food manufacturer is working with a supermarket chain. They're doing an experiment to compare pet food sales based on shelf height placement. This is important to both of them, since supermarkets charge for various shelf locations. They select 3 different heights and randomly select 8 stores for the height treatment for each group. Here's the results of the experiment. We have 3 different means for knee, waist, and eye height with the associated variances. And then we'll use this table to quickly compute the sums of squares. So the total sums of squares works out to 682.18. The sums of squares, let's see, 7 degrees of freedom for each group. So that takes care of that. And that works out to 303.8. And then we just take the difference there, and we get 378.38, more or less. Let's put this in the F table, in the ANOVA table now, and see how that works. So there's our sums of squares for treatments and groups and the total. Divide by the degrees of freedom to get the mean squares. And then we'll just take the ratio of those two to form what's called the F statistic. Now the F statistic follows what's called an F distribution, and under the null hypothesis, the expected value of the F is about 1. So large values of the F statistic indicate that there's a great difference in means, and we should reject the null. If we look at this F in the F table, here's our degrees of freedom. It has a degree of freedom for numerator and denominator. If we look that up, we see that our critical value is 3.467. Our test statistic is quite a bit larger, so we're going to reject the null hypothesis. The means are not equal. Now all we have to do is figure out which ones are different. To do this, we're going to use what are called post-hoc tests. Post-hoc simply means after the fact. So we want to see who's different. ANOVA can't do it. We've run out of gas with ANOVA. So now we're going to use the post-hoc tests. Contrary to what I said about experiment-wise error previously, we're going to use pairwise comparisons. But we still need to control for the experiment-wise error. There's lots of techniques to do this. We're going to do just 2 of them out of 12 or more possible tests. The 2 tests we're going to use are Chaffee's test, which is a very conservative test, but it requires no new tables, and the Bonferroni adjustment, which also requires no new tables, and it's just a variation on the t-test. Let me talk about those just briefly. Chaffee's test looks like a 2-sample t-test, but it's got a couple of exceptions. Instead of the pooled variance involving just the 2 groups being compared, we're going to use the mean square error, which is basically the pooled variance for all the groups, whether they participate in the comparison or not. This is a technique called borrowing strength, and it just gives us a better variance estimate. So this is a common technique used in statistics. The critical value, we don't have to get new tables. We're just going to use the ANOVA critical value and plug it into this computation right here. Bonferroni adjustment's actually even simpler. It's a 2-sample t-test. However, we're going to adjust the type 1 error. So we'll take our original alpha and we'll divide it by the number of possible comparisons. So this will give us a larger critical value. So let's take a look at this. Let's look at the example and follow it up. First, we'll do a comparison with Chaffee's test. So here's our critical value. So degrees of freedom for groups times the critical value. And if we bang this through the calculator, we'll get it 2.633 for our critical value. Let's compare just 2 of these, the knee and waist levels. So we'll take the absolute value of the difference of their 2 means. We'll divide through by the square root of the MSE times the sum of the reciprocals of the sample sizes. And when we turn the crank, we get 5.267. Okay, so that's quite a bit bigger than the critical value. And so knee and waist differ. If we do the other 2 possible comparisons, knee and eye and waist and eye, we get a small comparison for the knee-eye comparison, so no difference. Whereas with waist and eye, we get a larger test statistic, and so there's a difference. How about with the Bonferroni adjustment? Well, since this is a balanced experiment, we only need 1 critical value. What do we mean by balanced? All group sizes are the same. And this means that all of our 2-way comparisons will have 14 degrees of freedom, because 14 is 8 minus 1 plus 8 minus 1. Okay? I'm going to divide it by 6 because we have 3 comparisons, but it's a 2-sided test. Hence the plus minus. Let's compare the knee and waist levels again. So here's our t statistic, the difference of the means, and then in the denominator, the square root. of the standard errors for each group. So 13.14 over 8 plus 9.13 over 8. And that test statistic comes out to be minus 5.77, which is much, much less than minus 2.7178, and so they differ. If we do similar calculations for the other two comparisons, the knee-eye comparison has a relatively small test statistic, and so there's no difference. But the waist and eye comparison has quite a bit larger one, and so these do differ. Nice to see that the Chaffee and Monferroni tests concur. If you're the sort of person that likes formulas, you can look at this appendix at the end, and it shows every possible formula that you could use to do these calculations.